Have you ever tried to understand ordinal regression and felt completely lost? You are definitely not alone. Ordinal regression is super powerful, but it's also very confusing, poorly explained, and therefore often misinterpreted. Many tutorials out there just scratch the surface using a basic summary function that honestly doesn't tell you much at all. So in this video, we'll start with the reasons why summary function is horrible in explaining ordinal model. Then we'll solve all the limitations of it and extract the most knowledge out of ordinal models. We'll look at how to get the actual probabilities for each possible outcome, how to understand risk differences and risk ratios, a friendlier option than odds ratios, which confuse a lot of people, how to interpret cumulative probabilities, like what's the chance of getting a rating of 3 or lower, and how to find exceedance probabilities, meaning the chance of scoring above a certain level. Let's jump in. We'll use the free wine dataset from the Ordinal package to study factors affecting wine bitterness. We'll analyze wine ratings, an ordered response variable with 5 levels, 1 to 5, where higher ratings indicate greater bitterness, from 1, least bitter, to 5, most bitter. In R, we must define this variable as an ordered factor, so the model recognizes its ordinal structure. But what does ordinal actually mean? Ordinal means categories have a natural order, but the gaps between them aren't equal or measurable. That's why ordinal regression is often called an ordered Logit model. Examples include Likert scales, for example from strongly disagree to strongly agree, or severity ratings, for example mild, moderate, and severe. In this video, we'll use numbers 1 to 5, but these are still categories, not continuous values, so a rating like 2.7 isn't possible. Now, to predict wine ratings, we need a predictor, right? To make our model as intuitive as possible, we'll use temperature during wine production as a simple categorical predictor with only 2 categories, cold and warm. And at the first glance, it looks like the warm temperature is significantly associated with higher ratings, which means more bitterness. But let's build an ordinal model and see what it says. To build an ordinal model in R, you can use at least 5 packages besides the one I prefer in this video. I avoid those packages because they are weak in at least one aspect of model interpretation, and I want to save you time. A common choice in tutorials is the polar function from the mass package, which stands for proportional odds logistic regression, another name for ordinal model. This name naturally brings us to the proportional odds assumption, the key assumption to check to ensure the model is truly ordinal. Why check it? Well, because not verifying a model assumptions is like diving into a pool on a hot day without checking if there is water in it. To check the proportional odds assumption, you can use the Brunt test from GoFCat package. A not significant p-value greater than 0.05 indicates the assumption holds. A much better option though is the graphical method using the plotxmin ordinally function from the RMS package. It plots predictor means by order category level in solid line and expected predicted values, assuming the proportional odds assumptions is true, in dashed line. If the solid and dashed line track closely, our model's proportional odds assumption is solid and we're good to go. But if they start drifting apart, the graphical method is better than the Brunt test because it shows how much the assumption is off. Why does this matter? Well, it helps us decide if ordinal model is still okay or if we need a different approach. However, while checking assumptions is crucial, a slight violation of the proportional odds assumptions often still gives better results than using alternative models. But if the assumptions is badly violated, consider multinomial logistic regression, which doesn't assume ordered categories. You can feed this using the multinom function from the neural networks package, and I've just made a separate deep dive video on it. Now, I'm using the Ordinal package's Cumulative Link Models function for Ordinal Regression in R, where Cumulative Link Model is just another way to say Ordinal Regression. Why pick CLM? Because it's simple, clear, and pulls out the most insights from our ordinal model. Plus, it can easily level up to mixed effect models, but that's a story for another video. Today, we'll stick to a basic ordinal model. Since most tutorials rely on the summary function to explain it, let's start with that and see why summary function totally sucks. Imagine someone unfamiliar with statistics, or even an alien, trying to understand what the summary function does. It shows a single number called estimate for the warm temperature. But what is that number? Instead of calling it just estimate, why not call it what it actually is? A log-odds ratio. This would clarify that it's a difference, not an average or raw log odds, but a difference from what? That's the key question. It would be much clearer if the output showed both categories, cold and warm. So we could see that this log-odds ratio reflects the change from cold, which is actually the intercept, to warm. Right now, the summary function assumes we already know that cold exists, that cold is the baseline category, and that the estimate shows the change from cold to warm. Since we're stuck with the summary output, let's at least interpret the estimate of 2.29. It means that warm temperature, compared to cold, increases the log odds of a high wine bitterness rating by 2.29. But it doesn't specify which ratings, which brings us to the second reason summary sucks: threshold coefficients. Threshold coefficients are the intercepts for the unspecified cold category in the ordinal model. They are shown in confusing, unexplained log odds units and tied to a hidden cut point predictor that's not even displayed as a predictor. The imminence function from the imminence package clarifies it's the cold category. Subtract the warm coefficient, 2.29, from any cold threshold in the summary, and you'll get the warm thresholds. But the summary function only gives you half the info, without saying which half, leaving you to figure it out by yourself, which is so unintuitive. The final reason this summary function makes ordinal models confusing is that it doesn't give interpretable results like probabilities for outcome categories or even odds ratios. You have to manually calculate everything to get useful insights. For example, you need to exponentiate the estimate to get odds ratios. But what about probabilities for cold and warm temperatures? The probabilities for each wine bitterness rating? Or the cumulative probabilities of the thresholds, the heart of ordinal regression, and the differences between them? Here is a quick look at how simple it is to calculate cumulative probabilities and their differences using the imminence function. But since cumulative probabilities come from the basic probabilities of our outcome variable rating, we first need to understand and extract those basic probabilities from our model. Let's use the imminence function to predict the probabilities for each bitterness rating 1 to 5, based on wine temperature. By setting our outcome variable rating as an artificial predictor and using mod probability in imminence, we get the predicted probabilities for each rating directly. This is super useful for direct interpretation, because it provides the most intuitive and commonly desired output for ordinal models, the probability for each specific outcome category. How does it work? Well, with mod equals prob, imminence creates a pseudo factor named after the response variable rating, calculating probabilities for all ratings. It acts like an extra synthetic predictor, which we can plot on the x-axis to visually compare probabilities. Using the MIP function with temperature as a predictor and rating as the synthetic predictor in mod equals prob, visualizes these probabilities clearly. The results show that cold wine tends to taste less bitter, often getting a bitterness rating of 2, while warm wine is usually rated slightly more bitter, around a rating of 3. Moreover, the graph clearly shows that cold wine more often receives lower bitterness ratings of 1 and 2, compared to warm wine, while warm wine often receives higher bitterness ratings of 4 and 5 compared to cold wine. The fact that confidence intervals of warm and cold wine don't overlap suggests that there is a real difference between the two groups. However, relying solely on non-overlapping confidence intervals isn't enough to confirm a difference. To be certain, we need p-values to determine if the difference is statistically significant. And
that's where the magic happens.
Because we can compare the probabilities of preferring warm versus cold wine in two powerful ways. First, we can calculate the absolute risk difference by subtracting one probability from another. This is easily done for all ratings at once by adding only one word, pairs, to our probabilities. For example, using probability at rating 2, we can subtract 12% of people rated warm wine with 2 from 48% of people rated cold wine with 2 to get 36% difference, which can be interpreted in the following way. The probability of a wine rating of 2 is 36 percentage points higher for cold than for warm, and that's statistically significant. And since lower ratings means lower bitterness, we can conclude that cold wine is significantly less bitter than warm wine. Similarly, the probability of a wine rating of 4, which means high bitterness, is approximately 23 percentage points lower for cold than for warm wine, and that's statistically significant. Now, when is the absolute risk difference useful, and why do we need it? Risk difference is useful for quantifying the absolute effect of a condition. For example, how many more wines receive a rating of 2 under cold versus warm conditions, which is easier to interpret for decision-making than risk ratio, which we'll explore next. Risk difference is important when probabilities are high, as risk difference provides a clearer picture of the actual change in probability. For example, if we had two high probabilities, 90% and 95%, the risk ratio close to 1 downplays the difference and is less intuitive for practical decisions, while the risk difference of 5% clearly shows a 5% absolute difference. By the way, we can also compare ratings between each other inside of the cold or warm categories by simply switching places of the rating and temperature inside the immeans function. This shows that cold wines are most likely to be rated only mildly bitter at rating 2, which is 35 percentage points higher than rating 1, 42% higher than rating 4, and 46% higher than rating 5. For warm wines, there are no significant difference between the higher ratings of 3, 4, and 5. These results confirm that cold wines tend to be less bitter, while warm wines are more likely to be bitter. The second method to compare probabilities is to divide one probability by another, creating what's called a risk ratio, or relative risk. Risk ratios are easier to understand intuitively compared to odds ratios, which is why I've created 2 additional videos on this topic. A risk ratio is the ratio of how the probability of an event in one group compares to another group. For example, if we look at the probability data at rating 2, dividing the probability of cold wine, 48%, by warm wine, 12%, gives us a relative difference of about 4. To accurately compute risk ratios between groups in R, we need to perform some R-code gymnastics. First, we transform the basic probabilities into a specialized log scale for accurate statistical calculations in log odds. Then, we conduct pairwise comparisons on this transformed scale. Finally, we translate the results back to the understandable probability scale. Running this R code provides risk ratios that compares cold and warm ratings for each outcome, ranging from ratings 1 to 5. Interpretation is as following. The probability of a wine rating of 2 is 4 times or 300% higher for cold than for warm, and that's statistically significant. Similarly, the risk ratio of 0.77 indicates that the probability of a wine receiving exactly a rating of 3 is 0.77 times lower, or 22% lower under cold conditions compared to warm conditions. The 95% confidence intervals provide interesting insights here. First, they overlap visually on the graph, indicating there may be no statistical difference between the groups. Additionally, the interval includes the value of 1. This inclusion suggests that the risk ratio is not statistically significantly different from 1, the value representing no difference between the cold and warm groups, according to our null hypothesis. These findings aligns with a high p-value of 0.7. Unfortunately, the means function does not directly provide odds ratios for ordinal models, and I have not found another straightforward method to generate all odds ratios simultaneously. If you know a simpler way, please share your code snippet in the comments section for everyone's benefit. Even if you don't have a solution, consider checking the comments section in case someone else has already provided one. However, there is still a way to calculate odds ratios manually using probabilities provided by a means. We first convert probabilities into odds by dividing probability by 1 minus probability. For example, to find the odds ratio comparing cold and warm wines at rating 1, we calculate odds for each group and then divide one odds by the other. In this example, the odds ratio indicates that cold wine has about 10 times the odds of being rated the least beta compared to warm wine. Similarly, for rating 2, the odds ratio shows cold wine has 6.7 times the odds of being slightly beta compared to warm wine. With some basic R coding, we can generalize this calculation for every rating. But here is the question: do we really need it? Well, personally, I think odds ratios are much less intuitive than risk ratios. Risk ratios are straightforward, just one probability divided by another. In contrast, odds ratios involve dividing a probability by 1 minus that probability, and then dividing this result by another probability divided by 1 minus that second probability, which gets quite confusing. But when are risk ratios most useful? Risk ratios are particularly helpful for understanding the relative impact of a condition. For instance, how much more likely a wine gets a high rating under cold versus warm conditions. Risk ratios are especially informative when probabilities are low, as even small absolute differences can mean substantial relative effects. For example, a change from 0.01 to 0.02 doubles the risk, giving an risk ratio of 2. By the way, don't worry if you notice different p-values for risk ratios and risk differences. It happens naturally because each measure is based on different statistical tests and scales. Here, we can also compare the ratings among each other inside of every temperature to get risk ratios by switching the temperature and rating words inside of a means function. Moreover, since we usually don't report standard errors when we have 95% confidence intervals and don't use the degrees of freedom, null and z-ratio columns when we have p-values, we can remove them for a cleaner looking result table. Here is how to interpret one specific contrast. For cold wine, the probability of a wine being rated as mildly bitter, rating 2, is 22.57 times higher than the probability of it being rated as very bitter, rating 5. In other words, there is a 2,157% increase in the likelihood of receiving a mildly bitter rating if the wine is cold compared to very bitter. This substantial difference is highly statistically significant, meaning this finding is highly reliable and very unlikely to be due to chance.
Let me tell you something. Let me tell you something.
Understanding basic probabilities, as we've just explored, is crucial because they form the foundation for cumulative and exceedance probabilities, two key concepts in ordinal models. Once you know how they work, you won't be able to unknow it. However, this video is already quite packed, so to keep things focused, I've created a dedicated video on cumulative and exceedance probabilities, where we'll explore them in depth. It's really fascinating stuff and I think you'll really enjoy it. See you there.